introduce the principle of least action. And from this principle, we have derived the equations of motion known as the Euler-Lagrange equations, which are actually sort of a substitute for the literal equations of motion, in the sense that we could start all of physics from F equals ma, which is a basic equation of motion, and create all our models using these equations of motion. Or we could formulate the Lagrangian of a system, which we understood from our study of mechanics to be the difference between the kinetic energy of the system and the potential energy of the system. The difference, not the sum, right? Because for a conservative system, the sum would be a constant. And taking derivatives of a constant is kind of uninteresting. But the difference actually is talking about energy that's buried in the motion and energy that's buried in the potential. And from this, we can presumably, if our principle of least action is of any value, calculate an action that will be minimized by the ultimate motion of the system. And what else did we learn? Well, we learned that this integral here buries a lot of information, and it better, because it's basically telling us all physics, right? Ultimately, in this, there has to be enough richness for all of mechanics, continuum mechanics, classicals, mechanics of physical bodies, rotational motion, all that stuff. Somehow, we believe it comes from this, just like we believe that all of physics kind of comes from Newton's laws. Now, there's an obvious problem about relativistic versus non-relativistic, which is clearly this is non-relativistic. This guy here probably has its own relativistic and non-relativistic versions, and we're going to talk about that a lot today. But as a reminder, the ultimate answer here are these guys, right? We are looking for these generalized coordinates and the derivatives of the generalized coordinates. These things are functions of time, right? I don't have time explicitly attached to this, but there's no reason why I can't write q of t and q dot of t, right? And that's important because these are what we're seeking. This is the physical motion of the system. And it shows up in our principle as an argument to the Lagrangian, which is ultimately integrated with respect to time. These guys are functions of time. This is a function of time. So L ultimately is a function of time. So when integrated with time, you should end up with a number. And then if you complete the definite integral between two time intervals, you get the action. And then the principle says whatever functions of time minimize this action, those are the functions of time that answer the question. Those are how your coordinates evolve in time and how your velocities of those coordinates evolve in time. So this is what we're seeking. And I think we have a handle on how to interpret this, and we certainly have a handle on how to interpret this, right? Because we've got this integral here. The big mystery, of course, is L, right? L is the thing that gobbles up these functions and ultimately produces a clean function of time that can be integrated. So what the heck is L? And that is the subject of today's lesson. We're not going to do all of the amazing examples that are out there. You can study an entire course on Lagrangian mechanics, where all you do is construct Lagrangians for a wide variety of circumstances. You actually get past this, too, because you can introduce constrained motion. So it gets very sophisticated, not of which we're going to do literally none. Presumably, you've done all that, right? You've studied classical mechanics, you've studied it in its Lagrangian formulation, you've done all of these marvelous problems. We're kind of going to go back to the core essentials of coming up with Lagrangians for some of the simplest cases, that of a free particle. Hopefully we'll get through the free particle today, and then for a free particle with charge in an electromagnetic field, and that's the prerequisite part. It's all prerequisite for quantum field theory because understanding the Lagrangian is critical because the quantum field theory is inevitably expressed as a principle of least action, and we're always building Lagrangians for fundamental fields, and so if we stick with the fundamental particles and then start thinking about fundamental fields, we'll be in great shape. So let's begin with the non-relativistic free particle and see how you might construct such a fundamental function, such a basic function that we could suspect might satisfy this requirement, meaning that put into this integral gives us a least action. What could it be, right? And that is, so let's begin with that subject. So we begin our story with the free particle, right? The free particle. We're going to study the relativistic and non-relativistic case. Actually, the non-relativistic first. And the reason why we're going to do this is it's a little bit of a philosophy, right? We're talking about, so here's a particle, right? Moving. What possible properties could this thing have? How hard can the Lagrangian of a free particle possibly be? Well, a free particle can certainly have position in space, and it can have speed or velocity, right? It has velocity, which means speed in various directions. So it has location, a speed. It probably has a property called mass, which we derive from basically Newton's musings about how velocity force is proportional to acceleration by this concept of mass. But a free particle can't have a lot of other things. It could have charge, right? So it interacts with a magnetic field or electric field. So we're going to imagine the free particle, of course, doesn't have magnetic or electric field interactions. It's just moving all by itself under the influence of just space, right? And space is defined as the thing which does not offer any influence. So as you can see, to study what a Lagrangian for such a particle would be, if you're going to start from scratch, you've got to say, well, what do we mean by free and particle, right? What do we mean by space, and how big is this particle, and measurement? And there's so many philosophical puzzles in here that this is the place where we have to make those philosophical choices. And this is also true in field theory. In field theory, you ultimately are building Lagrangians out of some philosophical choices by what we mean by free fields, interacting fields, how do we mathematically describe them. And this is one of the reasons field theory is hard, is because you have to build these things up from so almost philosophical scratch. And people think you're not. People assume that it's done, in some sort of systematic way. But it's a bunch of guesswork and experimental analysis. So the free particle, what's our first piece of guesswork? Well, our first piece of guesswork is that we believe space is homogeneous. So we believe that whatever the Lagrangian is of this free particle, if you calculate the action in this part of space, the part that the pointer is circulating in, you better get the same minimized actional as if you calculate the same Lagrangian over here in this point of space. That is, if a particle if a free particle has a certain type of motion in one part of space, that motion must be demonstrably similar in another part of space. And similar means the action functional must yield the same values for q of t and q dot of t. You better get the same motion described over here as you do over here, right? And so the reason that that's a puzzle is because, the point in space, the point has coordinates. That's a property of the point, is the coordinates. And the point over here has coordinates. Now you start thinking, well, I could just sort of change coordinates pretty easily. That's not a thing. But if it could be a thing, right? You could imagine that, you have some sort of building on the on the Earth, and this building is like normal building called N. And then you have another building, but it's not normal. It's like very special building that, maybe this is like a special building we call S, and it's like a holy place or something. So we could ask, well, if you move a particle around inside a holy place, is that different than if you move it around a normal building, right? If you do an experiment on the Earth, is it the same as if you did the same experiment on the moon, right? Well, if it's different, if the Lagrangian of a particle here is different than the Lagrangian here, which is different than on the moon, then space is not homogeneous. So we're going to assume space is homogeneous. And with that assumption, we basically are now looking at a Lagrangian, which could be a function of space, and the particle has a position, in other words, right? the particle's generalized coordinates are just the position coordinates. Its generalized velocity are just those positions with derivatives with respect to time. But now we say, you know what? It can't be a function of position. It can only be a function of velocities because we assume that space is homogeneous, right? So that is the first thing that we learn because we believe space is homogeneous. This is a physical assumption that we're making. We're going to find a Lagrangian based on that physical assumption, and then find the action functional and hope it works. So is that enough? No, we have other things that we believe. We believe that space is also isotropic. And isotropic is a way of saying that every direction in space is the same, right? So if I were to move in this direction in space, space has the same impedance to my motion as if I were to move in any other direction in space, right? It doesn't matter which way I'm going, which way the particle is going, space is not going to impede the motion any differently in any different direction. Because remember, all we're talking about is a free particle, so all we can talk about is your motion through space, right? That is the answer to the question. How does a free particle move through space? And now we know that it doesn't matter where in space you ask this question. It also doesn't matter what direction of motion you're interested in. Space is isotropic, so our Lagrangian should also reflect the isotopy of space. And the way we realize this is that, okay, we've gotten rid of these variables, and we have x dot, y dot, and z dot, but if the Lagrangian depended on x dot alone, say, then somehow the Lagrangian prefers or is interested in your velocity in the x dot direction more so than the y dot direction. And it can't be. It's got to be completely equal-minded, right, between these three directions. What's the right word for equal-minded? What am I looking for? The word I'm looking for is egalitarian, right? The Lagrangian must be completely egalitarian with respect to x dot, y dot, and z dot. Otherwise, space would not be isotropic. Therefore, the Lagrangian must be a function only of v dotted into itself, which is v squared, or some function of the absolute magnitude of v, but we always write it v squared, which causes a little confusion later. Well, not confusion, but a little bit of a complication later on, but nothing significant. The point is because it could be a function, say, of the square root of v squared, which is just v, for example. So this doesn't really reduce our flexibility very much. But the fact is that space being isotropic and homogeneous has eliminated these variables and taken these guys and crushed them into a single one. And now we're left with the Lagrangian as a function of v squared and possibly a function of time. So let's consider the function of time now. We also have an additional sort of assumption that if I perform an experiment right here with a free particle, and I observe, basically, performing experiment is awfully heavy-handed way of saying I'm observing a free particle's motion, right? Because you can't perform much of an experiment if you're dealing with a literal free particle. All you can do is watch its motion. So you study the motion of a free particle, and we've already decided if you study that motion here, you're going to come to the same conclusions that if you study it there, and that means the action functional is the same here as it is here. So if you sort of set up a coordinate system here, right, and you studied the motion of this particle inside this coordinate system, if you took that whole coordinate system, shipped over here, and studied the same motion, in both cases you will end up with the same value of q of t and q dot of t, right? Notice that you're still looking for q of t, even though it's not in the Lagrangian. The generalized coordinates are a thing. They're just the Lagrangian doesn't depend on them, right? And likewise, the generalized coordinates of these, the generalized velocities, right, of the generalized coordinates, they are a thing that you're looking for. It's just the Lagrangian doesn't depend on it, independently. It only depends on this combination of them. But the point is, whatever you get for these guys down when you did the experiment over here, it's going to be the exact same answer that you got over here. So that was the homogeneity. Then, of course, we talked about isotropy. But the idea also is that if I do this experiment here today and I do it tomorrow, then I will still get the same answers, right? So the Lagrangian, depending explicitly on the time, means that the Lagrangian kind of depends on when you do your observations. And we don't think that matters. We don't think the laws of physics are changing on a day-by-day basis. And when I say the laws of physics, what I really mean is we don't think that the motion of a free particle in space depends literally on when we do the test, right? If Galileo does the study of the motion of a free particle and Richard Feynman does a study, they're going to get the same answer, despite the fact that they lived a few hundred years apart. So, because of that, we can kind of get rid of this time. So, time does not enter into the Lagrangian either for a free particle, right? Remember, all this literally depends on our idea that we're dealing with something super simple, like a free particle. Okay, so what's the next principle? Now, the next principle is where we really make our money, and it's also the hardest one. It's relativity. We are going to introduce a principle of relativity, and this is really what's going to tell us the most specific thing about our free particle. And the idea of relativity is totally bizarre, because what you're now saying is that if I conduct an experiment in a frame of reference, not just a frame of reference in one place and then in a different place, or not just a frame of reference that is, say, differently oriented, right? Those are the two we've already covered. Doesn't matter what orientation I do my frame of reference, and it doesn't matter where I do my frame of reference. Homogeneity of space and isotropy of space. But now I'm saying, oh, no, wait. If I actually had a second frame of reference, right, and that frame of reference is in motion with respect to the first frame of reference, and I took my free particle and I put it in this moving frame of reference, right, then the experimental results, my observations with respect to this moving frame of reference, are going to be the same as with the original one, unconditionally, right? And that's the hard one to figure out. This is the one that just doesn't make sense. Actually, isotropy of space is already a problem. If this is the ground, right, we kind of know that the direction down is not the same as the direction up or left, right? You have this gravitational attraction to the ground makes isotropy very hard to figure out. You have to become a very abstract thinker to understand isotropy of space. Likewise, position too. If you have a sensitive measurement, you might realize that a position down here is different than a position up here, and that gravity is weaker or stronger. That wasn't really a thing that the classical physicists of Galileo's day understood, of course. I don't think they ever realized that gravity was weaker the higher up you were. They just assumed everything fell, right? But the point is that that's already pretty hard. But imagine trying to figure this out as a classical physicist in the early days, that a body in motion remains in motion unless acted upon by a force. That's the principle of Galilean relativity. And that notion of relativity means that if we take the velocity of our particle, our particle's velocity, and we just arbitrarily add a little bit of velocity to it, and then, and this is a constant amount, right? This amount doesn't change, right? The velocity of the particle changes according to the laws of physics that we're trying to figure out. But this delta V is not going to change. We should be able to get a Lagrangian that doesn't, or a action functional that's the same, and the same equations of motion in this moving frame vis-a-vis this stationary frame, right? And this is a Galilean relativity principle. So this really informs our Lagrangian a lot. And let's see how. And the first obvious, well, nothing's obvious here in my opinion, but the first thing you do is if you're going to transform the velocity of a particle by a fixed amount, remember this is a finite constant amount, but it's small. We're going to go with small. And small means that if we dot it into itself, we get a number that's tiny enough to ignore. So the Lagrangian, which is some function of the velocity squared, is now going to have to become a function of the velocity of the particle squared plus this little chunk that's dependent on this incremented velocity that we add to it. And this little chunk is all part of the Galilean transformation of the velocity. Now this piece we're going to ignore because we've already agreed that delta V is small. And this means delta V dotted into itself, just like this means V dotted into itself. So this part goes away, and we ignore that part. And then we basically linearize what's left, right? We take this piece, the Lagrangian of V squared plus do V delta V, and we linearize it. But remember, we're considering the Lagrangian as a function of V squared. So we're taking its derivative when we linearize it with respect to V squared, right? Don't let that confuse you. This isn't a second partial derivative, of course, but because you don't have a square here, right? This is literally taking just the just the partial derivative of L with respect to V squared. Now, the other part that's a little puzzling here is that L now, we've got it down to a function of a single variable, V squared. So this notion of a partial derivative is a little awkward. However, almost always when we talk about the derivative of the Lagrangian, we're talking about it as a partial derivative. So I'm going to kind of leave it in there because we could be wrong, right? There could be other things in there maybe. But we're going to go with, I'm going to leave this as partial derivatives for now. It's really unimportant because all we're talking about is linearizing this expression by taking, we know that this is the large part and this is the small part. So that part is so small we ignore it. This part is linear small, and so we can do this linearization. So with that in mind, we remember that the action doesn't change if you change the Lagrangian by adding, remember, a total time derivative of some function. You could have any function in the universe, and if you take its total time derivative and add it to the Lagrangian, the action is not going to change, ergo the law of physics are not going to change. So the question is what does it take for this to be a total time derivative? Because that becomes a constraint on L. This is a constant, so there's nothing we can do about that. The velocity that's a property of the particle. That's part of the that's a property. We can't really change the property of the particle, but we can change the Lagrangian in such a way, or we can select a Lagrangian in such a way that this whole piece becomes a total time derivative. And the way we do that is we're looking at just this part. We write this as dr dt, right? V is dr dt. And notice this is not a partial derivative. This is a total time derivative. And I'm saying, well, if I want this whole thing to be a total time derivative, then I have to move this ddt out front, right? I have to be able to take this ddt and put it out front here. But if I did that, I'm in trouble, right? Because this becomes a product rule where I have to take this time derivative. I have to take the time derivative of this function, right? The partial derivative of the Lagrangian with respect to v squared, multiply by r dot delta v, and then add to it this derivative of the Lagrangian times d r dt delta v. Remember, delta v, this is a constant, so I don't have a third piece of my product rule. And the second part of that product rule is, in fact, what we have, right? Because that v is dr dt. So that first part's got to be 0, which ultimately means that whatever dl dv squared is, it can't be a function of the velocity. If this was a function of velocity, then d by dt of that would give you an acceleration, right? If any function of the velocity, there would be acceleration type terms. So dl dv squared just can't be a function of v. And if that's the case, then you can pull this ddt out and you end up with this guy here, this guy here is a function of, this guy here is, this is equal to that, which means this is a total time derivative. And remember, to identify this as a total time derivative, I just have to find any function out there of which I can take the time derivative and get this thing. And that's not hard to do, but one absolute requirement is that dl dv squared is not a function of v. So what does that mean for us? Well, if dl dv squared is not a function of v, the only possibility is that L of v squared has to be some constant times v squared. If I take the derivative of this with respect to v squared, I just get alpha. And it's not a any other function of v or v squared, or any other additional term that involves v squared here. For example, if I added the square root of v squared, right? Or if I added v to the 3/2 or something, which would end up being v cubed, right? Those derivatives with respect to v squared would leave v's behind, and if you leave v's behind and you took the total time derivative, you'd end up with accelerations. So that can't be there. So ultimately, this tells us that the Lagrangian has to only be a function of v squared. So this is our third step. We got to the Lagrangian's only a function of v squared. Our fourth step, right? Because we also had that time step. So we had homogeneous, isotropic. Then I invoked time, which I guess could have been a third one. I don't know why I didn't include it as a third one. But then relativity. And that leaves us with just this. So now the question is this constant of proportionality. And the way we handle these constants of proportionality is we just look at experimental results. And so now, And in this case, our experimental results is we believe that there's a thing called momentum, which is the mass times the velocity. And we define momentum in Lagrangian mechanics as the derivative of the Lagrangian with respect to the time derivative of the associated generalized coordinate. You got to remember this. This is the canonical momentum idea. And, if L is actually alpha v squared, then dl dv squared is going to be alpha times 2v. So in order for this thing here to actually equal the momentum, we pick alpha to be 1/2 m. Pretty common way of looking at this is the way we choose this constant proportionality has to be based on experimental evidence. And so that's how we get that. And just for completeness, if we look back here, imagine taking the Lagrangian of the sum of two velocities, right? The velocity of, say, the particle and then the velocity of the reference frame transformation. This becomes alpha times v1 plus v2 squared, which is this vector expression here. And that becomes alpha v1, which is our original Lagrangian. And then I can find an h of position and time such that its total time derivative equals what's left, right? Because I've chosen this, right? I'm now sort of proving that I can find such a function that is a total time derivative. So now I know that this function, the function of the sum of two velocities, is just the function of the first velocity squared plus this total time derivative. So this form definitely works pretty well. So that tells us in the end, ultimately, that our final result here is that the Lagrangian equals 1/2 mv squared, which is the kinetic energy side of things. And the point of all this was to get you to exercise this notion that we're really going to guesswork, right? This is all guesswork. The part that's not guesswork is understanding that our action principle does not change when we add a total time derivative to things. This concept of things that, transformations that don't change things, is just so profoundly important in physics in general, but in field theory in particular. It becomes this heavy-hitting idea of gauge transformations and things you can add to the Lagrangian that don't change things. It comes up over and over again. Isotropies and general relativity. Or gauge transformations in electromagnetism and gauge transformations in field theory. It's just such a ubiquitous idea that you really, really got to get used to it. And here's a good elementary implementation of that idea that's very, very profound. It also shows you how important the notions of relativity are in our formulations of physics. In this case, it was Galilean relativity, but look how rich it was. Even though Galilean relativity is wrong, we still derive all of Newtonian mechanics straight from this. So now, if you use this Lagrangian, right, well, we know that you use this Lagrangian, you end up with F equals ma as your equation of motion. So that, if you run this through the Euler-Lagrange equations, you end up with F equals ma. For example, here's the Euler-Lagrange equation. Remember, one of our generalized coordinates was x, so the generalized velocity is x dot. Well, dl dx dot, just make our substitution for L, which is 1/2 x dot squared plus y dot squared plus z dot squared, right? That's the v squared piece. The derivative with respect to x dot squared. Clearly what's going to happen is this term here is going to go away. That term's going to go away. The derivative with respect to x dot squared is going to be just 1/2 m, right? Oops. Sorry. The derivative, this derivative is not with respect to x dot squared, it's respect to x dot, right? See, the formula is with respect to the derivative is with respect to the generalized velocity, not the velocity squared. It's a function of v squared, right? The Lagrangian is a function of v squared, but the derivative is just with x dot. So here, what do I get? I get the derivative with respect to x dot is now mx dot, right? This guy, the derivative is all 0, right? This is not a function of x at all. So we end up with mx dot equals 0. No, that's not right. No, now we have to take the derivative with respect to time. Boy, it's been a long time since I've done this. You got to take the derivative with respect to time, and you get d by dt of mx dot equals 0, which basically means the change in the momentum in the x direction, right, dpx equals 0, which means the momentum in the x direction is a constant, right, which is the conservation of momentum. Now, we should go through this whole thing about conservation laws in the principle of least action and Lagrangian. We will, but not right now. But the point is this is, our equation of motion has been validated, right? We have validated our equation of motion, and by experimental evidence, right? We know that momentum is conserved for a free particle in free motion, and this would have been true for x, y, and z. The point is this Lagrangian is validated, right? We used basic principles: homogeneous space, isotropy of space, homogeny in time, I guess is a way to say the other one, to get rid of the time variable. The Galilean relativity, being the most important, gets us all the way to here for a free particle, and then, kaboom, we actually use the Euler-Lagrange equations. This is the implementation of the principle of least action right here, right? This came from the principle of least action. Like I said, you'll never calculate S, right? We're never going to run this integral. Let me. Of course, eventually there will be occasions to engage more directly with the action itself. The point is that the principle of least action is used to give us these equations that will ultimately give us this, which is the equation of motion. This guy here is the equation of motion. It's the manifestation, or the execution, not manifestation, the execution of the Euler-Lagrange equations given the correct Lagrangian, which we derived this way through our philosophical principles, right? Okay, so That's the point of doing this for a free non-relativistic particle. And where did non-relativistic come in? It came in because our principle of relativity was Galilean. So now what happens when the principle of relativity is no longer Galilean? All right, so now we're going to look at the relativistic free particle. And you might think that, well, we just have to somehow modify the non-relativistic case. But the problem is a little bit deeper than that. We have to understand, relativity really changes everything we think about when we think about this sort of stuff. So here we have our coordinate system, and I'll put one coordinate x there to represent all three coordinates and, of course, time. And the idea is that a relativistic particle, the way we understand it is that it moves along a world line, and I'll just draw some arbitrary world line here, and it starts at some time t1, and this world line ends at some time t2. And this is the path, this world line, this is the path now that we're interested in. We're no longer interested in like a literal path in space. We're actually interested in this world line path through space-time. So we have to remember that what we're dealing with, and this should be a review, is that the position x is a function of some parameter, which we could call, let's call it sigma. And the position in time is also a function of sigma. And sigma is basically a parameter that kind of measures where along the world line you are, right? So that would be, say, sigma 1 and sigma 2. And, sigma 3 gives you this value. So for example, x of sigma 2 is this value right here. And t of sigma 2 is that value right there, right? It's just the coordinates of this point along the world line. And these world lines are what you are seeking when you solve problems in special and general relativity. You want to know where is the position at every time. And this time t is in the laboratory that you're executing your study. It's the clock in the laboratory that you're studying. Now, when this becomes general relativity, all of this becomes a little more subtle because this time t is now some arbitrary time that is called the coordinate time. And, well, it's always the coordinate time, regardless of whether you're studying special or general relativity. But the notion of the coordinate time is much more subtle in general relativity and much more interesting. But the point is that this is now what we're after, is these functions here. Notice that before, time was not a function of anything, right? Time was the parameter. Now time is parameterized by this thing we're calling sigma, which somehow represents where you are along this world line. So that's fundamentally different, right? That's part of what special relativity and general relativity is all about, is changing the perspective so time is treated just like space, right? So the trick is, it's this world line is what's important. So getting a handle on what we're going to call sigma is the intuitive thing that you learn or is the thing that we need to develop intuition about. And it is what we learn in special and general relativity very quickly to understand. And so that understanding that we need to take to this problem is that this guy here, we're going to understand it in our context, the special relativity context, to be the proper time of the particle itself. So let me back some of this stuff up. So the idea is that if I had a clock attached to this particle, and that clock, let's see, what does a clock look like? There, that's better. If we had a clock attached to this particle, and the clock moved along the world line of the particle. So now, notice, first of all, our particle is still a fundamental particle. It only has these properties in mass. So the idea of having a clock attached to it is a little weird. What we're really saying is that you and I in our lab are moving along with the particle, and in our laboratory, the particle is just sitting there at the origin still. And we're observing it, we're looking at it, and we have a clock, right? So that's the idea. We're always moving in such a way that our frame of reference is on the particle and we have our own clock. And that clock's ticking is the proper time, right? That clock's ticking is the proper time of the particle. The particle can't have a clock because if it did, it wouldn't really be elementary. It would have pieces and motion, and this becomes part of the philosophical issue that we're trying to deal with. So anyway, so we have this particle, and now it's moving along its own world line. Now, this motion on the world line is determined by an action principle, meaning if we knew what the action was of this particle, if we knew its Lagrangian, we would be able to use Euler's equations and figure out exactly what these functions here are, just like we did before. The fact that it's relativistic is not particularly important with regard to the principle of least action, that is. But what I'm trying to get at here is that this parameter sigma that we have here is going to be the length of this world line. The length of this world line measured in meters, right? I have time here, which seems to be seconds, but what you'll usually see is that'll be a CT, or sometimes they just call this x0 and measure it in meters, and they set c equal to 1, right? We'll probably play around with both of those ideas, but the point is the length of things in a space-time diagram, just like in the beginning part of the class when we talked about special relativity and the paradoxes, this length is measured in meters. And that length, the length along this line is invariant, meaning no matter what coordinate system I'm in, the length of this world line should always be the same. It's a Lorentz invariant in special relativity. So that brings us back to this question of the relativistic free particle. What are the philosophical assumptions that get us into this Lagrangian? And the first is that the Lagrangian must be Lorentz invariant. And when you look at this motion that we just talked about, there's one obvious Lorentz invariant that just jumps out at us, and that's the length of the world line, right? So if we were to calculate the world line between the beginning and the end, or calculate these infinitesimal little pieces of world line, right, we immediately have a Lorentz invariant. So let's keep in mind that that's the simplest and most obvious thing that just jumps right out at us. And so considering that, how can we take advantage of it? So we know that L must be Lorentz invariant, and we're thinking, you know what, that world line probably has a lot to do with L, right? And we're also thinking that, well, it is still a free particle, so whatever we're dealing with should be relatively simple, and you can't get simpler than that length of the world line. So why don't we try to say that our action is just some constant proportionality multiplied by the length of the world line in space, right? Or in space-time. And the length of the world line is just some differential ds, some little increment of the world line integrated from the beginning of the world line to the end. That's certainly the simplest thing we can imagine in a relativistic case that is Lorentz invariant, because this length is Lorentz invariant. So the length of the world line is also the same as the amount of proper time from the beginning of the path, the proper time at the start of the path, to the proper time at the end of the path. If I kept track of the proper time along that path, that is the same as the length of the world line. That is the definition, almost, of the length of the world line. So we know that this guy is this sort of put in terms of the proper time of the lab moving along with the particle. And then I can transform that to any lab, like the lab that's watching the particle, by using the laboratory time and correcting by a factor of gamma. Now remember, gamma depends on the velocity of the particle, the instantaneous velocity of this frame. This frame is accelerating, right? This frame that's moving along with the particle, at every moment, it's got a slightly different speed, right? Because clearly the particle is going very fast here, and then it slows down and it's motionless here, and then it goes fast the other way here, and then it goes really fast here. Now, the way I've drawn this, by the way, you see that this is sloped greater than 45 degrees, which if this scale was the same as this scale, this would be faster than the speed of light. So obviously, my time scale is not the same as my space scale. In fact, if I was to do this so that they both had the same scale, I would draw it more like this, I guess, right? And even right here is a bit questionable. I guess that's definitely better than 45 degrees. So this is more of an accurate world line, although this is pretty fast if this scale and this scale is the same. Anyway, so this now becomes our candidate for the action functional, meaning that this alpha dt over gamma becomes the candidate for the Lagrangian. And if I put in this gamma here and I set c equal to 1, so beta equals v over c, but c equals 1, regardless, either way you want to look at it, we now have this as our candidate action functional with this guy here as our Lagrangian. And boy, what a simple Lagrangian this is. And then if I actually plug in the v over c, I get r dot squared over c squared, right? That's what beta, that's my replacement for beta. So c is now not equal to 1 anymore. So this is sort of two different units. I love mixing unit systems. That's my annoying thing. That some people like it, actually. They like when I show different units and different notations all in the same lecture. It sort of bucks the trend of how this is usually done, but nevertheless. So now here's our Lagrangian right there, right? And let's see. So this implies, when you do this, if this is our choice, look what we get. A Lagrangian for a particle where a particle ostensibly has only the properties of its position. So this would be x1, x2, x3, all expressed in vector form. And this would be x dot 1, x dot 2, x dot 3 expressed in vector form. Just like this was, right, back in the non-relativistic free particle, right? So this here is really literally the same as this here. But if you look at it, it all comes down to just r squared, right? And notice this is the Lagrangian here, not this dt. There's no t in it. So we've already, just by doing this one step, this one choice of Lorentz invariance and trying to stick with the simplest thing we can think of, we immediately get isotopy of space and homogeneity of space. And we get homogeneity in time too. So there it is, right? So this is exactly the same kind of statement that we got before, but now we actually get the function itself, right? Before, with isotopy and homogeneity, remember, we got LV squared once we did the homogeneity in time, but all we know is that it is a function of v squared. We had to actually introduce relativity to get that it was proportional to v squared. Well, here, I guess we've actually done the same thing, because by demanding Lorentz invariance, we've chosen this space-time interval or the length of the space-time path to be our Lorentz invariant Lagrangian, and embedded in that right away through our understanding of relativity and the definition of gamma, we end up in the same place. But we know literally what the function is too, and it's no longer proportional to v squared like in the classical case. It's equal to this thing, right? So now with that in mind, we want to figure out what alpha is, right? Alpha is still an unknown constant, and we use the fact that the conjugate momentum has to be gamma m0v, right? We know therefore the derivative of the Lagrangian with respect to the generalized velocity r dot, where r dot represents any one of the three component velocities. If you take this derivative, the derivative of this thing here, I think I did it here, right? You get The 1/2 comes out from the square root. The square root goes from 1/2 to minus 1/2, so it gets thrown into the denominator. And then you take the derivative of this, and you get 2r dot c squared to the minus 2, and then alpha comes with it too. So that's the derivative of this expression right here with respect to r dot. And so you get minus gamma alpha c to the negative 2 v. Right, that's what this is. I'm now putting this in sort of vector form, so it's v. And so for the only way to get this to equal gamma m0v is to choose, let's see, alpha to be m0 c squared, right? So that's how we do alpha. Again, sort of an experimental thing, right? We understand what momentum is. We know that we have to have a conjugate momentum that gives you the standard momentum, or I should say this, we want the conjugate momentum of this to give you the standard momentum. So you choose alpha to be m0 c squared. And so now I can write down the Lagrangian in full form, m0 c squared over gamma. And now notice I wrote gamma as a function of v squared because it is, right? There it is right there. Whoops. Function of v squared, right? That's r dot is v, so I'm just going to write it as v squared. And that minus sign comes from this right here, right there. So alpha has to be m0 c squared for this to work. Wait, is that right? No, that's not right because the minus sign here came from this derivative. So I have to get rid of that minus sign to match. So alpha has to equal minus m0 c squared. And then our Lagrangian is correct, right? Our Lagrangian is correct. Yeah, so alpha has to be minus m0 c squared. And so this is the Lagrangian, and then if you blow the Lagrangian up by just Taylor expansion, you're basically Taylor expanding 1 minus r squared over c squared. You end up with minus m0 c squared times 1 plus 1/2 minus m0 c squared r prime squared, and the c squareds cancel, and you get minus 1/2 mv squared, right? So you end up with wait a minute, I kind of think I'm feeling like the sign here is wrong because I want this to end up being this positive part being the classical result. Yeah. I screwed this up, right? Gamma's in the denominator, right? So if gamma's in the denominator, this is the square root of 1 minus v squared over c squared. The Taylor series of that has a minus sign here, right? I did the Taylor series of 1 over 1 minus v squared over c squared, which would be gamma up here, right? So I screwed that up. So there's a minus sign there, and the point is that L now it's minus m0 c squared and then plus, and the result is m0 basically v squared 1/2, right, which is the classical result. So if you keep the first order term here, you end up with the classical result. Not the first order, the second order term, I think. But regardless, you get that classical result with this constant up front, which is the legendary E equals mc squared thing, right? Okay, so now understanding that we have basically accomplished finding the correct conjugate momentum, establishing what the conjugate is, or what the constant is, determining what the Lagrangian is, we can note a few things. One is the momentum, this is the momentum we were after. If we fool around with this a little bit, we get that, let's see, p squared equals m squared beta squared. If I turn c squared into 1, then v ultimately has to go to beta, and then this is literally beta squared. And then I did some calculation here, and I figured out that beta squared is p squared over m squared plus p squared in units where c squared equals 1. And the reason that's important is because I can write the Hamiltonian of the system. Remember, Hamiltonian dynamics is pq dot minus the Lagrangian, which becomes gamma mv squared plus mc squared over gamma. And if I work that, by pulling out gamma mc squared, v squared over c squared, 1 over gamma squared, this becomes 1 minus v squared over c squared. That's what 1 over gamma squared is. And you just do the math and this all cancels and you end up with gamma mc squared, that is what the energy of a particle is, right? The Hamiltonian is the energy of a particle, and we know that the energy of a particle in relativistic mechanics is gamma mc squared. So this should be a bit of a review. We are going to do a deep section on relativistic mechanics, because that is a critical part of understanding field theory, because ultimately field theory is a lot about scattering, and scattering is all about relativistic mechanics. But as a little bit of a prelude, this Lagrangian gives us the right total energy also, which is fun. And if we really push that, this becomes m over 1 minus beta squared, where in the units where c squared equals 1. And then that beta squared, that's where I take this guy that I calculated, beta squared equals p squared over m squared plus p squared, right? And I get m over square root of m squared plus p squared, and I end up with the Hamiltonian, or the total energy, is the square root of p squared plus m squared in units where c equals 1. And this comes up quite a bit in our study of field theory, in particular when we cover the the Klein-Gordon equation and the Dirac equation. So our Lagrangian, calculated from these basic principles, this Lagrangian right here, seems to do the trick. Right, so that is the Lagrangian of a free particle. I guess I should put a box right around it right here. I'm going to put a box around it, right, like that. That is the Lagrangian of a free relativistic particle. All right, so in our next lesson, now we're going to take this idea, and now we're going to start adding the most elementary interaction. That is the interaction of a free particle with charge and an electromagnetic field. And the goal of that isn't really to understand as much about the Lagrangian of the free particle in that condition, although that is an absolute byproduct of what we're going to do. We're going to try to understand how to understand the electromagnetic field's Lagrangian, because we got to add to this Lagrangian a piece that involves the electromagnetic field. And from there we're going to learn how to deduce the electromagnetic potential, the 4-vector potential, and from that, so we're going to learn how to derive this idea, the A mu, right, which is the electrostatic potential and the magnetic vector potential combined as a 4-vector, right? And then from that, we're going to understand how we get the electromagnetic field tensor, right? And this is the relativistic invariant quantity that we really need to understand to set us up for a comprehensive understanding of field theory. So the reason we're doing this is, first of all, people don't have a good grasp on where this guy comes from. And I can't promise to give you a good grasp, but I will show how this kind of logic applied to a velocity-dependent potential yields, using very basic logic, yields this as a very reasonable thing to consider. The problem, of course, is that it's not unique, but it will produce ultimately an electromagnetic field tensor, and that is relativistically invariant, and we'll be able to formulate Maxwell's equations in a relativistically invariant setting. I don't want to say it that way, because Maxwell's equations are relativistically invariant. What I want to say is they're manifestly so, right? It's manifest. That's the language they use. It's manifestly invariant, which means you can see it obviously. Basically, manifest is a word for saying if you see space-time indices, it's Lorentz invariant. That's sort of another way of looking at it. But anyway, we're going to get through to this, and that's our prerequisite concept. All right, so that's what we'll do next time, the electromagnetic field Lagrangian.